Time is 9:30. Let's get started here. Okay, so just as a reminder, project number 2 is due at noon on November 7th. We will talk about the exam here in a few seconds. And also just as a reminder, we will have a regular lecture-based class here today because when I was recording my lectures last year, again, we did not, for some reason, have any sound recorded when I had this corresponding lecture, so we're just going to have a regular old lecture here today. So let's talk about the test here. As you saw from my listener post, the grades are relatively good. Sure, I'd like to have a little bit more of the B's moved up to the A's, but overall the median's 87%. So those who did fall in that B range, we had a lot of high B's. Okay. So overall, I thought the tests, the overall scores in general were good. Let's see here. Now make sure that you do look over my entire answer key, even if you got a particular problem right. Look over how I actually approached the problem. In particular, there were a number of problems, such as, let's say, number 1, where there could be different ways to answer it. And so I think it would be very helpful for you to see how I answered it, especially how succinctly I answered it in comparison to maybe to some of you who wrote a whole page on answering it, which was fine, as long as you can finish the test. But I think maybe perhaps less could have been said on some problems, in particular number 1. Also, just as a reminder, please try to write neatly on the test. For many of you, it was extremely difficult for me to read your handwriting. And this actually resulted in a loss of points a few times because I just couldn't figure out what you're writing. I know it's you have a certain amount of time that you have to complete the test, but if you can't do the basics of writing it so that I can read what you're writing, that's obviously a problem. Also, I do recommend that you use pencil instead of pen. I know whenever I took a statistics course in grad school, I always used pencil because it was a lot easier to change my answer if needed, rather than if I were to use pen. You can still use pen, of course, but I recommend using pencil. Now, there was just one problem that I wanted to discuss with respect to the test. This was by far the most missed problem. This was problem number 3C. I've given this problem before on a test, maybe not with this exact same data set, but I've given the problem before a number of times on a test in a multivariate course, and I have not had these kinds of I guess the degree in terms of the number of students who have missed this problem. So I was quite surprised by it. Most of you who did miss the problem approached it from the point of view of you just ignored the data set itself. And you just wrote out, when we first were talking about how to insert the orthogonal matrix in the factor analysis model, you could do some math with it and eventually get to new factors. But since this problem relied on a particular data set, you need to answer the problem with respect to this data set. And with that, then, it's actually fairly simple. Just take your factor loadings that you get from the model without any kind of rotation at all, and take it times a particular orthogonal matrix, which is actually given to you through fitting the model with the Varimax rotation. And just for emphasis, I did put a particular page number in the notes where we did do this for you to see that. Okay. Other than this particular problem, there really wasn't one overall question problem on the exam where a number of students were having difficulties. So if you have any questions about how to do a particular problem on the exam, please feel free to ask at this time. If, however, you have a question about why I took off a certain number of points on a problem, please ask me that individually after class. Are there any questions at this time about the exam? Okay, let's move on.
regarding the count number?
About the what?
Total right. I mean total right score.
The total right score?
In my case, the ball is not included.
Okay, well just bring that up to me after class. I apologize if I can't count. I do have an undergraduate degree in mathematics, but sometimes that doesn't work.
Well, maybe, like you mentioned, this problem 3C that we had to answer with respect to the data set. However, for example, in question 2C, right? For example, when I was solving the test, I looked at the problem 3C, and I thought, well, maybe you need the numbers, right? But you said, you know, the 3C sounds very general. So then I looked at 2C, and in 2C we don't need to do anything with
well, but that plot's given to you, and that plot is based upon the data. And with respect to what you would see in that plot, and hopefully what I was hoping is that to answer 2C, you would actually construct the plot. Well, you didn't have to, but definitely it would have helped you if you would have actually then constructed the plot that included then the colors and the numbers as well. So given that there was at least the plot there, yes, it's with respect to the data. I can see your point how it is kind of a more general question too, but it is with respect to this particular data set itself. You know, there are three categorizations for these weak kernels. So,
Can you further discuss the answer of 2D?
to what?
2D.
2D. Do you have a specific question regarding the problem?
What's the answer?
What's the answer?
Yeah.
It's in the answer key. Well, you know, I'm sorry to say this, but you should always look at the answer key first before asking a question.
Yeah.
And after you look at the answer key, if you still have a question, I'll be more than happy to answer it. Yes? 2C? Okay, do you have a specific question regarding 2C?
I think the answer, yeah. For example, the group categorization of the cat level.
Yeah.
So I don't understand the answer, but do you consider the type of the kernel?
Well, yeah, I mean, you know, there are three types of the kernel. It's very similar to the serial data set when we colored by shelf in the notes.
Sort of bias. You don't need the component.
You don't, I can't hear you. I'm sorry.
It's kind of biased.
It's kind of biased.
I think.
How is it biased?
Like, we don't know the categorization of the kernel.
Yeah.
Of a given type.
Yeah.
But we don't come up with that result by looking at one.
Well, that's kind of the purpose, is to add that information to the plot, just like you did with the serial data that was in the notes. And the whole purpose, you know, one of the big purposes of principal components was so that we could see, you know, the data in a smaller dimension, so that we can make judgments about it. And in particular with the serial data, we wanted to make judgments about, well, are certain shelves organized in a certain manner? That's kind of like what the weak data does too. We have these pre-known organizations or categorizations of the kernels. And so, but you know, since there's a lot of variables, obviously you can't just do one scatter plot of all 5 or 6 variables. So what do? We could do a principal component analysis, and then also look at, you know, maybe there's certain trends with respect to the categorizations in that 2D representation or 3D representation, just like with the serial data.
So in the answer, how do you color the observation?
Just like with the serial data. You could use the, I believe it's the FG argument with the symbols function.
No. I mean, by looking at data set, by the colors, according to one.
Well, what are you coloring with respect to? The categorization.
Yeah, according to type.
which is exhibited in the type variable, which is given at the very beginning of problem number 1. If you would like, we could talk more about it after class. So I think we were kind of going in circles here, and I'd be happy to talk to you individually about it. Are there other questions? Okay. So in the notes, then we would leave. Based upon the previous video, we left off on page 39. We were just getting to the goblet data set, and we were going to apply hierarchical cluster analysis methods to the goblet data set. So, obviously it's probably been maybe a little bit since you last looked at hierarchical clustering, so we'll do a little bit of review too as we go along with this example. Excuse me. So here's the old goblet diagram here. If you remember what we do with this data, we actually take all the variables, except for x3, and divide by x3. And thus we are left with 5 variables overall. Notice that all the variables then remaining have something to do with the width of the goblet, except for variable 6, which corresponds to the height of the base. And what we're interested in, since, especially since there's no pre-known categorizations of these goblets, we're looking for, with this cluster analysis of, well, maybe there are certain types of categorizations that we can make. After all, if you maybe you don't use goblets every day, but you do use glasses or other kinds of containers that hold, let's say, liquid or other stuff. And sometimes there's small, like juice glasses, and there's bigger, other kinds of glasses as well. Then you could even go to buckets, you can go to other kinds of things, other kinds of containers. So what we're hoping is that, in this archaeological dig, is that we can somehow categorize these goblets. And so let me go ahead and take a look at tin then. Reading my data the usual way, and similar to what we've done before, I'm going to adjust the data, take into account the overall height, and then I am going to find the standardized data as well using the scale function as we've done many times before. Okay, now the first thing that you have to do with hierarchical clustering based upon the functions that we're using for it is that you actually have to find what you could say is a distance matrix. Meaning you need to find all pairwise distances of the observation. So you need to know what's the distance between observation 1 and observation 2. The way that we typically measure distance is through standardized Euclidean distance. So with my standardized data that's in Z, I use my dist function to find the Euclidean distances. And so if I just show you the matrix real quickly, page up, we can see, for example, the standardized Euclidean distance between observations 1 and 2 is 2.64. Okay. Next, to do the actual clustering, we use a function called hclust, hierarchical for h, clust for clustering, where we put in the distances in the D argument, and then we have to specify one of the 5 or 6 hierarchical clustering methods that we have discussed before. In this case, I'm just going to use nearest neighbor. I picked that because it's the first one I introduced to all of you, not because necessarily that this is the best method for this particular data set. And if you remember, nearest neighbor has a particular another name to it that some people refer to it as, and it's called single linkage. And hclust does use this alternative name, so that's why I use the single option for method. I put the results into clust.nn. And then, so that we can see the process itself of how clusters are joined, I decided to create a data frame where I put in the information about how clusters were merged with the actual distance between the clusters. Now, in a standard analysis, you may not really need to do this. I am doing this for demonstration purposes. Okay? Imagine, let's say, if a situation where you have 1,000 observations. Well, you might not want to see how all 1,000 observations were joined together in clusters. Okay? So first, the first cluster that was joined corresponds to -3 and -16. Does anyone remember what that negative there means?
An observation.
Yeah, it means it's an observation. So actually, observation 3 and observation 16 were joined together, and they had a standardized Euclidean distance of 0.4018. Next, then, observation 6 and 14 were joined together. And if we keep on going down here, let's actually go here, we see a -19 and a 2. What does that mean? Observation 19 and cluster number 2, which means observation 19 was joined with observation 6 and 14. And here was the corresponding distance. Okay. Next, let's actually do, yes?
So if you go back to that
Sure.
output and you look at that distance matrix for the third row and the 16th column, does that give you the distance?
Third row, 16th column? You mean, I don't know what you mean. Are you talking about this right here?
He was saying up with the matrix.
Yeah, those are columns. So if you
Oh,
look
I'm sorry.
in the
Yep.
for the third and 16th observation distance, if you plug those indices in, will you get that distance back?
You should, yes.
Okay. So I was kind of playing around with it, and it was returning something different, but perhaps I was mistaken.
Well, give me a specific example. You can post it to the listserv. I'd be happy to look at it. Okay. Let's see here. So then with the, yes?
So by looking at the data set, can we find out the distance between observation 19 and 6?
That data frame that I showed you before? Yes. If they were actually joined together, I don't remember. Observation 19 and 6?
Yeah.
No, because notice 6 and 14 are joined together.
Observation 19 and 4.
Excuse me?
Observation 19 and 4.
19 and 4?
Or 14. I thought it was 6.
Observation 19, based upon the nearest neighbor method, okay? Observation 19 was joined with cluster 2 with 2, which consists of 6 and 14. Since we are using the nearest neighbor method itself, then this 0.59 should correspond to the distance between 19 and 6 or 19 and 14, one of the two. Okay, now we're going to do a hierarchical tree diagram using the plot function, and this is what we come up with. Let me actually just go over here to Word because I should have it in here. There we go. So we have a hierarchical tree diagram, and this basically gives us information in a hierarchical sense, you could say, of how clusters were joined together. So if you remember, that first row of that data frame consisted of observations 3 and 16. Was it 3 and 16? Just to verify. Yes, 3 and 16. So that data frame that showed the whole process of how the clusters were joined, 3 and 16 were joined first. So notice with this hierarchical tree diagram on the very bottom, we see that they are joined and joined at a distance of 0.4018. I'm just pulling that off the data frame on page 40. Okay. Next, what was joined was 6 and 14. You see that 6 and 14 here, and that corresponds to a distance of 0.454. So we see the whole process. And the reason why we look at this hierarchical tree diagram is to make a determination, well, how many clusters are appropriate for this data set and this clustering method. Again, I'm not saying that this clustering method was the best, but for this clustering method, using this hierarchical tree diagram, let's figure out, well, how many clusters are needed. And what you do is you look at basically, where you see maybe larger distances between successive clusters to make that choice of where you cut the tree. So I simply used the AB line function, and I decided to cut the tree at this location here. Because we see this distance of successive clusters that are being joined as somewhat large in comparison to other clusters that were joined. So for where I have that red line there, how many clusters does this represent if I cut the tree there? 3. Simply all you do is you count the number of times that horizontal line intersects that tree diagram there. So what this is saying is that perhaps 3 clusters are appropriate for this data set with this clustering method. Next, I decided to cut the tree here as well. How many clusters does that correspond to? 6, yes, exactly. This can be difficult to figure out because notice, this line's not intersecting for 23 and 24. So you have to take into account, based upon, and not every software package draws the trees exactly like this, but what R does, it actually will move then the observation numbers up kind of to where that joining occurs. Where I think, it's been a while since I used this, but I think SAS actually puts all the observation numbers here, down here, and so you would see long lines that go all the way down. Just the way it's done, there's nothing wrong with it. But you just have to be careful. Does everyone see why it's 6? Any questions? Okay. So I drew that line there because, where I see successive clusters being joined, this seems like a larger distance there than comparison to around it, in terms of maybe for 5 clusters or 7 clusters and so on. Now, what could be a potential problem, though, with using 6 clusters in this particular case? Some of the clusters have few observations, meaning essentially a number of the clusters just simply have 1 observation. In fact, that's 4 clusters. Perhaps that might be okay, but I think you'll see in some plots coming up, you'll be questioning whether 6 is really appropriate. Okay? But I at least wanted to point that out now. Cluster analysis, we want to group like observations together. And hopefully, if I have 1 observation, I have another observation that's like it. Now, sure, there may be situations where you have an outlier that's completely different from all the rest. Yeah, then that might be okay to have a separate cluster just for that 1 observation. But oftentimes, you don't want that to occur. You're trying to find groupings that make sense relative to the data. Another possible set of possible clusters. I drew another line there. This is I think somewhat iffy. This corresponds to 1, 2, 3, 4, 5, 6, 7, 8 clusters. But notice here, I did not draw a line here. I didn't think I drew a line there. Well, just from the plot, look at for 3 clusters in comparison to 2 clusters, where that new red line that I just drew there. We can see that with 3 clusters, there was a larger distance than for 2 clusters. So I don't think it's necessarily as justifiable to do 2 clusters in this situation in comparison to 3. From just look at the hierarchical tree diagram alone. You can say something similar to, well, why didn't I draw a line here? It's for a similar reason. Look around it. We see larger gaps, like for 6 than what we would for, I guess that would be 5. Yeah. So that's why I chose the lines at those locations than these new horizontal lines that I just drew. I'm trying to emphasize that because I think, as I said last time, that this is where some of my students were having difficulties last year. They did want to draw lines like right here at times. Okay. let's see here. So previously in the videos, I talked about this this rect.hclust function, which allows you to draw rectangles around certain clusters. You can see that on your own. I typically do not use it, but you're welcome to use it if you want to. What I want to get down to is on page 44. We're going to talk about using now principal component analysis to help us justify or determine the number of clusters that are necessary. Why? Well, again, we have 5 variables to look at. And if we could, it would be nice if we could do, let's say, a 5-dimensional scatter plot, and that we could actually maybe, have, let's say, the plotting points correspond to the clusters that we've chosen. So in that case where we had 3 clusters, you could colorize those points in 5-dimensional space by the 3 different separate clusters. And that will help you see, well, does it make sense to have these observations in these 3 clusters? Obviously, we can't draw a 5-dimensional scatter plot. So what we can do is combine what we learned before with principal component analysis and basically look at a smaller dimensional representation of our data and maybe do a 2D scatter plot, a 3D scatter plot using 2 principal components or 3 principal components in terms of their scores, and then use that to help make a judgment of, well, does it make sense to use 3 clusters? And so what I've done to help you out is I've written a function called pca.ca.plot, which basically takes what we learned in the principal component analysis section, uses printcomp, finds the scores in the appropriate way, does a 2D scatter plot, does a bubble plot, and then also does a 3D scatter plot as well. And also it colorizes the points corresponding to the number of clusters that you pick, or that you specify, I should say. I want you to take a look at this function on your own. I'm not going to go through it here in class because it's just applying all the stuff that we've learned before. I've just kind of grouped it all together in a cluster, in a function. Let's instead take a look at how to actually implement the function. Simply with my pca.ca.plot function, I specify my data set. Here's my data. I specify where my cluster results that I've obtained before are found. And I specify, well, how many clusters do I want to look at in these plots? And I put a nice little title here to help me identify, well, what these plots correspond to. And then when I run it, we have all these nice little plots come up. I'm actually going to go over here to words so I can write on the plots. Let's actually make this a little bit bigger for us. Yeah, let's remove that. There we go. Okay. So let's take a look at the plot on the left-hand side here. I have principal component number 1 on the x-axis, principal component number 2 on the y-axis. I hope you can see this. Is it clear enough that you can distinguish the points? So circles, pluses, and triangles. Is it clear enough, or do you need to make it bigger? Be a little bigger. Let's see what I can do here. So I almost did 1,670%. That reminds me of something that really frustrated me last spring. I was using a software package called, oh, shoot. Now this frustrates me too, that I cannot think of this software package off the top of my head. JabRef. Anybody used JabRef before? It's a nice little software package that allows you to put bibliography references in it, and then you can, in Word or LaTeX or LIX, you can call references from a reference file. Anyway, I was using that software package, and I had accidentally said to zoom like 1,000 or 10,000%. And I was zoomed so much, I could not see in my software package of how to unzoom it. it frustrated me for a long time. I had to actually post a message to the JabRef listserv, and someone said, "Oh, well, you have to go into the what's it called in Windows, the registry, and change something there." I was able to do that. Unfortunately, I cannot use the software. Anyway, I hope you can see this. I don't think I can really blow it up anymore because then we start losing labels. At the very least, you have it in your notes. And so what we see here is that we have observations 23 and 24, 4, 5, 17, and then these remaining observations here corresponding to our 3 clusters. And this kind of makes sense. 23 and 24 are kind of away from the pack of the other points, as are 4, 5, and 17. It's somewhat questionable, but what do you do with 18 here, or maybe even 10 and 22? But using 2 principal components, which I should also mention was somewhat justifiable based upon what we did in the principal component analysis section for the goblet data. So I feel as though I'm okay looking at just 2 principal components. And we can see there's some justification for having 3 clusters. It's definitely not perfect, but some justification. Let's look at then using 3 principal components. And this was also somewhat justifiable. I think this got us up to about 94, 95% of the total variation explained. With 3 principal components, it was like 86%. So the coloring there of the actual bubbles correspond to was the 3rd principal component positive or negative? So what do you think? Do you think blue corresponds to positive or negative?
Negative.
Negative, because those are the smaller points based upon how we've done these plots in the past. The bigger points then are the ones that are positive, and they are indicated in red. And so the actual then color of the observation number then corresponds to the cluster itself. And so, definitely we can see more about why 23 and 24 are in their own cluster in comparison to what we had over here. Because we see, in comparison to 10 and 22, we can see that, that 3rd principal component really makes some differences between the two sets. We can also see why 4, 5, and 17 might be separated from like 18 as well. That 3rd principal component. But what we also see is that, notice how 3rd principal components tend to be greater than 0 in large down there in comparison to those maybe up here. To some respect, this is saying maybe you need 4 clusters. Now, our hierarchical tree diagram did not really suggest 4. And so maybe this is an example of maybe nearest neighbor is not going to identify the clusters as good as maybe other clustering procedures. Any questions about that?
Just kind of a question about the plot itself. Is it possible, instead of having the different colorings, because like to me, I think that's really confusing.
Okay.
But I mean, can you do it in a different way where can you change the line type of the bubble? Or anything?
I've never actually tried to change a line
so
type
you
of the
don't have
bubble.
like color of bubble and color of text. I mean.
Yeah, maybe you could do the color of the bubble. Take the color of the bubble
Right.
out in terms of the positive or negative part, and actually make it the corresponding cluster. You could do that.
Okay.
I just chose to do it.
Yeah. I mean,
What would be nice is that maybe if you could change the symbol itself.
right.
But I have not tried that, or I should say that. I probably have tried it. I don't remember trying it, but I have probably tried it because it's an obvious thing.
Right.
And I want to say you cannot, but I could be wrong.
Okay.
Yes?
Suppose you are saying you are calculating the nearest neighbor in three dimensions. PC1, PC2, PC3.
I'm not calculating nearest neighbor in 3 dimensions with respect to the principal components. That's something you need to make sure you understand. I'm actually calculating nearest neighbors with respect to the 5 variables that we have. This plot gives us a 3D approximation to it. So that's something you have to realize. So let's say, and I'm going to talk about this more later, but let's say that 3 principal components only represents 50% of the total variation of your data. You can still do a plot like this, but you will probably more likely maybe see maybe observations that seem to be close together that are not maybe in the same cluster, because that principal component analysis is saying is that while you do have an approximation to your data, it's not representing the data maybe as well as you would like. And so that's something you have to watch out for. So be careful with judging exactly distances in this plot. Just remember that this is an approximation to our 5D representation, and relatively speaking, this should be a good approximation because of the amount of variation that's being explained. Other questions? The key thing is that we need some way to visualize what's going on, and these are particular ways that you can do it. They are not perfect, though. Okay, so let's take a look at our 3D scatter plot here. Okay, so again, I've colored the points corresponding to the actual cluster, so we can see these. This is 4, 5, and 17 down here. This is the green are the 23 and 24, and it makes sense. Look at the green, look at the red, why they are somewhat separated from the rest. But we also see this possible behavior of maybe we need this 4th cluster. Look at the blacks here. Now look at the blacks there as well. They are somewhat different. Perhaps they should be in different clusters. And I say perhaps. Let's see here. So one thing I wanted to point out, I believe, let's see. So let's look at 18. So again, we saw that 18 itself, just from looking at the 2D representation, you might think, well, maybe I should go with 4, 5, and 17. Excuse me. But then when we come over here, we saw, oh yeah, principal component number 3 is quite different from 4, 5, 17. Let's look at that with respect to this plot here. So here's 4, 5, and 17. Now, observation 18 is actually this point. Which one is it? I'm sorry. It's actually this point here. So just what we're seeing with that bubble plot over here, we're seeing the same thing occur in this 3D dimensional plot. Maybe you think it's overkill, and well, we see the same thing on the 2 plots, but I guess I like to look at it both ways. Okay.
Chris?
Yeah.
Is it possible to change the size of those points on the 3D graph? Because you could add.
Yeah, you could add basically.
Dimension.
Yeah, you could add a different dimension. I'm sorry to say this, but I'm not for sure. I have a feeling that you cannot, but I am not 100% sure. But yeah, that would be interesting to have essentially a 4-dimensional bubble plot. I know that there are ways in SAS to do that. I have done them, but I have not done them with the this particular package.
I bet you could do conditional labeling with like the text 3D. It wouldn't change the size, but maybe you could do some kind of labeling.
Yeah, you could somehow, if it's not possible to change the size of the plotting point, you could, incorporate some kind of label that would help you somewhat identify a 4th dimension. Okay, so page 46 then. So now here's 6 clusters. So just to help you out. So those are my 6 clusters, if I were to use 6 clusters. And we can see some of the issues that we saw with the hierarchical tree diagram, where we have these clusters that just simply contain one observation. And I think relatively speaking, you would think at least here that 23 and 24 should be joined together. They seem to be somewhat similar. They're out from the rest in about the same spot. But at least this nearest neighbor procedure says, okay, don't do it. But at least only look at the hierarchical tree diagram alone, you would think, yeah, there's justification for having 6 clusters. So I think this is an example of what maybe nearest neighbor is not the best. The reason why we talk about all these different kinds of clustering methods is that not one method is going to be the best in all situations. So typically in an analysis that I would do, I would actually apply multiple methods and then look for a method that gives me results that are reasonable in terms of what I can see, at least with these smaller dimensional representations, these smaller dimensional approximations, what I can see from that makes sense relative to the clusters that were chosen. Yes?
Why don't you merge the observation 23, 22, and 10 into one rather than
10, 22, 23, and 24?
no, 23, 22, and 10. Leave the 24 alone.
Well, I mean, just from looking at it in the 2 dimensions, that makes sense. But, look at how they have big differences when it comes to principal component number 3. So that's probably why they were not. And again, I don't necessarily have control over that. It's the clustering method that makes that determination. Okay, let's move on here. Let's make sure we talk about all the comments. So we already talked about the first bullet. Second bullet. Well, what should you do if 2 or 3 principal components don't necessarily explain enough variation of the data that you are comfortable with looking at plots of just 2 or 3 principal components? Well, you could still look at those plots just with the understanding of, well, maybe your approximation to the data is not as good as you would like. But I wouldn't have a problem with looking at the plots even if only, let's say, 50% of the variations explained. I just have in the back of my mind that, yeah, you just got to be more careful in interpreting it. But what you could also do is do some of these other graphical techniques that we've looked at to graph multi-dimensional or multivariable data, multivariate data. In particular, a good one that can be very helpful is a parallel coordinate plot. So this is represented on page 48. I have the lines in the parallel coordinate plot corresponding to cluster. So for example, we see those red lines there, that corresponds to observations 4, 5, and 17. The green corresponds to 23 and 24, and the black the rest. So this is with showing 3 clusters. And I think especially with this plot here, you can see some justifications for why the clusters were chosen. And also you can come up with maybe some interpretations for the clusters. That's eventually something that you want to do. If I say these goblets are similar to one another, you need to tell someone, well, why are they similar? Well, they are similar because they're all overall large in size. Or maybe they have a large top to it, but a small bottom. And in fact, that's what these reds and greens represent here. So notice with the reds, you typically have large values throughout the entire plot in terms of W1 through W6. And so these are large clusters. Large goblets. But look at how the reds differ from the greens, though. Both the greens are also large with respect to W1 and W2. Those were actually width of the top of the goblet. But look at the bottom of the goblet, which corresponds to 4, 5, W4, W5, W6. They are small. So these are goblets that have big tops but small bases. And then, the rest of the goblets, then you could say, well, let's say maybe they're kind of in the middle in size to small overall. But you definitely see, the differentiation between the reds, the greens, and the blacks. And it all has to do with, I guess, being up here on the plot. Okay? So from looking at this plot alone, it makes sense to me why the nearest neighbor method did divide up the points the way it did. Not saying it's necessarily perfect. Maybe there's justification for, for example, maybe this observation being in the greens. The only difference is, well, it's not as low as the other ones. I wouldn't be surprised if that was like number 22, maybe number 10, number 22 probably. Okay. Let's see here. So again, overall, when you have looked at some of the after you've use H+, you've done the hierarchical tree diagram, done some of these plots of the data to try to make sense of what the clusters are, and you come to a point where you're comfortable with the number of clusters, then you do the cluster interpretation, similar just to what I did here. And that then concludes the cluster analysis. Again, for emphasis, I would still try other clustering methods to see what those results are. But if I were only able to do nearest neighbor, then this gives you the whole process. Is there a question?
So let's say we have a binary data and the observation can take on the true or false, or 1 and 0.
So what would happen if you have binary data? Is that what you said?
Yes.
Okay.
So probably we don't have a, if I'm not wrong, we cannot have on the PCA on binary data.
You can still apply it. You can still do principal component analysis on binary data. Now let's say, just to make things simple, let's say you have only 3 variables, 3 original variables, and they're all binary. Okay? You could do principal components still. Now, how many different, let's say, principal component scores could you have? Well, there's going to be a finite number because you have a finite possible combination. So there's 8 possible combinations with 3 binary variables. Okay, so looking at like one of the plots that we did above, you got to be careful about. I might incorporate some jittering into the points being plotted, so that I don't have all the overlap of the the finite number of points that one would have. So yes, that obviously, when you just have the categorical data such as that can somewhat limit doing some of the stuff that we do here, but there are certain kinds of fixes that you could do, such as the jittering, to help you out. I'm not going to say it'd be perfect, but you could. Okay. So then page 49 then shows, well, what would happen if you use just Euclidean distance itself, not standardized Euclidean distance. Let's see here. I'm going to let you look at that on your own because it kind of just follows the same steps that we did here. Now, typically, again, you would use standardized Euclidean distance for all cluster analysis applications. But in situations such as with the Goblet data set, it may make sense because all the variables are measured on the same numerical scale. So please take a look at that on your own. Okay, so let's go to page 52. We're going to talk about non-hierarchical clustering next. Yeah.
So when we do hierarchical clustering, so we check into the dendrograms and then we check the PC scores and then we do the parallel coordinates plot.
Yeah. I mean, there might be cases where you don't do the parallel coordinates plot, you just rely on the PC scores. Or there might be situations where you can't do the PC scores, or you're maybe not comfortable with it, I should say, and only do the parallel coordinate plot. I mean, you could even do a stars plot too, but I think that might be more difficult to look at than a parallel coordinate plot in this kind of situation. So let's talk about non-hierarchical clustering. So with hierarchical clustering, it was called hierarchical because we kind of, join observations together, essentially one by one, and then joining clusters one by one, and kind of proceeded in a sequential hierarchical manner. Here with non-hierarchical, we don't do that. There's many different non-hierarchical clustering methods out there. We're going to talk about the most popular one because we don't have time for everything. We're going to talk about k-means clustering. The k correspond, in terms of we will actually use it as a symbol, will actually correspond to the number of clusters. Now, a characteristic then of this method is that we actually have to specify how many clusters you want to use to begin with. So, you might be thinking, based upon what we just did with hierarchical clustering, it's like, well, how can you do that? Because we don't know how many clusters we're going to have to begin with. Well, yeah, that can be a problem with this method. I will show you some ways that you can kind of get around that as being a problem later on. But at least initially, I would like you to think about, yeah, that is a big difference. And somehow you have to know before, like with the goblet data, I think we should have 3 clusters. You have to make that determination. But here's an advantage then of applying this method in comparison to hierarchical clustering. With hierarchical clustering, you have to find all pairwise distances between observations. Now imagine if you have a big data set. Let's say you have 1 million observations. How many pairwise distances would you need? Quick, do the math in your head. 1 million choose 2. Imagine if you have 10 million, 100 million observations. You can see the problems. With k-means clustering, you don't need to find all pairwise distances. So this is an advantage. So it can be quicker with the bigger data sets. So here's the process. So basically what I have, I just kind of, this starts on page 53. I just made up kind of a data set where I could simply do some simple drawing on, actually I did this in PowerPoint, do some drawing with some X and Y axes to help demonstrate the process of how k-means clustering works. And so let's say that I have just simply 2 variables. Let me make this a little bit bigger here. I simply have 2 variables. They're standardized. So I will typically always use standardized data again. They're called Z1 and Z2. And let's say that for some reason I chose 3 clusters. Here's a scatter plot of my data. Just even the red points there are actual observations. So both the red and blue are actual observations. And I like to apply then k-means clustering to this, where k was equal to 3. The process then starts with randomly selecting 3 observations from your data set to be what are called cluster seeds. The reason why the word seed is used because essentially we're going to grow the clusters around these seeds or grow from these seeds. So let's say we just simply have R choose some observations and those are denoted in red there. Okay? Next, find the standardized Euclidean distance between all the remaining observations with the seeds. So what that means is I'm going to find then the distance between, let's say, this observation and that seed, this observation and that seed, this observation and that seed, this observation and that seed. Okay, so I still have to calculate some distances, just like what we did with hierarchical clustering, but just not as many. So now, using all those distances that you find, group the observations with the seed that it's closest to. So, we see these 3 observations are closest to the bottom seed here. So that's why I drew a line around that to represent my green cluster there. This red seed there is closest only to that particular observation, so I grouped it there. And then with the last seed here, you can see then the corresponding cluster that I formed to. Now you might be thinking, well, wait a second, this observation looks very close. Well, no, never mind. I don't want to say that. again, I just put these points in PowerPoint and I kind of just visually judge. These are not actual observations that I had R formally do this with, okay? So based upon my perception of distance, these look the closest together. Yes?
So if we have an idea about the data set, let's say the ideal characteristics of the observation.
The what?
Ideal characteristics of the observation.
Okay.
So it can be a hypothetical observation as you see and start with the K close seed.
You can specify particular seeds on your own. Yes, you can do that. I have not had a reason to do that in actual application, but you could do that. I'd be worried, let's say maybe from a submitting a paper to a journal perspective, if you say, I specifically chose this as a seed, this is a seed, this is a seed, you need to really, really be able to justify why. There may be situations too where, I think of this from a, let's say, a marketing perspective. Maybe companies like Target, well, I should say maybe, they do. Companies like Target or maybe other companies that are very interested in their customers, they might want to say, okay, we are just going to figure out the best grouping into 5 different categories for our customers. Okay? Where, this particular category is going to represent this kind of person, and then you can specify maybe a particular seed to get that process started. So you could do that. Okay, so I have found some initial clusters. K-means clustering is actually an iterative process. And so what's done next then is a new cluster seed is found based upon the clusters that we have just formed. And the way that this new cluster seed is found is through simply finding the means of the observations in the clusters that you just had previously. So based upon where I saw the clusters forming, you can see now here are my new seeds. They do not have to be observation numbers now. They are simply, so for example right here, this represents, let's say, Z1 bar and Z2 bar for the green cluster. Okay? So that's where the name K means clustering comes from. Yes?
And we get our original observations back, right? Those don't go away now that we've kind of changed the seed.
Yeah, I mean the original, yeah. So that's why you see, for example, this right here. That was an original observation. So now what you do is you look. With these new seeds, let's grow the clusters again. Let's try to find the observations that are closest to these new seeds and reform our clusters. And that's what I do here. So again, you're using standardized Euclidean distance. So you find, let's say, the distance between this observation and that cluster, the distance between this observation and that cluster, the distance between that observation and that cluster there. Now, based upon how I drew out this plot, notice that this observation now has changed clusters. It is, at least in my perception of distance, it is actually closer to this seed than that one. Okay? Yes.
So the new seeds are no longer actual observations.
The new seeds do not have to be observations. Now, yes?
So the seeds are pretty much the centroids of the clusters?
Now, we repeat the process because now since this cluster has changed and this cluster has changed, we find a new cluster seed that's based upon the mean of the clusters. And then you reassign point observations to those new clusters, and you repeat this over and over and over again until you get to a point where observations do not change clusters. And then you stop. That's how K-means clustering works. So, I mean, the idea is fairly simple, but it is iterative.
So you have to decide how many clusters you want
Right.
and you cannot change the number of clusters.
At least in a direct implementation of K-means cluster, you cannot change it. I will talk about ways that you can justify, let's say, 3 clusters or 5 clusters coming up. That is actually different from what we had talked about prior clustering. And so, I guess to foreshadow, what can be done, and for example, is that you could rerun this process for 2, 3, 4, up to maybe 10 or 20 clusters, and there will be a particular numerical value that we can look at to help us make a judgment of, should I use 3 or should I use 4? Which is better? Okay, so let me talk about some notes on page 55. So I already talked about the first note. Let's talk about the second note. So an equivalent way to think about how this algorithm works, I don't think it's as good of a way than what I just talked about, but an equivalent way that actually is going to be helpful later is that you can think of this algorithm, what it's doing is trying to minimize what you could say is the within cluster sum of squares. Now in your Stat 801 type background, you've all learned about sums of squares, like for example with ANOVA and even regression analysis. And so you're looking at sums of squares basically helps measure variation, and what we're trying to do is minimize the possible variation that could occur in this plot based upon whatever you've chosen K to be in terms of cluster, membership. And so this is what the within cluster sums of squares looks like. We've got 3 subscripts here on X. So X is, I could write right in terms of the Z's too. X is our original data. The R subscript corresponds to observation number. The I subscript corresponds to variable number. And the K subscript corresponds, that's a little k, corresponds to the cluster number. And so given a capital K, number of clusters, we are trying to minimize then the distance, you could say, that X is from then the cluster mean for variable I. So you're essentially finding the mean across all observations in a cluster. This is a distance, you could say. We square it so that they're all positive. We sum over all the variables, over all the observations, and over all the clusters. We are trying to minimize this. That's what this K-means clustering method is trying to do, which hopefully makes intuitive sense. Because we don't want to assign an observation that's far from, let's say, cluster number 1. We don't want to assign it to cluster number 1. If we did, look what's going to happen to this measure. It's going to be big because the distance at X R I K is from X bar I K is going to be big. That's what we're trying to do. But this K-means clustering algorithm, it does not actually guarantee that you will find that minimum, meaning that you will not find the clusters or the observations belonging to a particular set of clusters. You're not guaranteed to minimize this. We would like to minimize this. The method's trying to minimize it, but it may not minimize it. Instead, what it might do is find what you could often refer to as a local minimum. Now, let's talk about what I mean by a local minimum. This will come about in your algebra days, but definitely, maybe in your algebra days, but definitely in your calculus days, in terms of classes you take it. Let's say I simply have one variable x, and it's and I have f of x with it. Okay, so outside of the cluster analysis realm here, and suppose I have something like this. This is my function that I'm graphing. We can see that the overall minimum corresponds to this x right there, right? Here, though, we see how the curve jumps down, and this is called a local minimum. It's not the overall minimum, or I guess the corresponding x is not an overall minimum, but it's a local one. And what this algorithm does is actually finds a local minimum. It will always find a local minimum. The question, though, is, and it may not necessarily ever be known to us, is this local minimum equal to the global minimum or overall minimum? Okay? So what can you do? That corresponds to this next point here. Obviously, when we started off, we just kind of randomly chose some points. So you might think, obviously, that this algorithm then is dependent upon what you choose for the seeds. And yes, indeed. If I chose different seeds, I could have got different clusters. And maybe find some other clusters that actually result in the global minimum, well, that sums of squares, than a local minimum. So, what can you do then? Well, rerun it. Rerun the process again. Let R, or whatever software package you're using, do the cluster analysis again and see if things change. Do my cluster memberships change? Do I get a smaller value for that sums of squares? If I do get a smaller value at sums of squares, then you might be thinking, okay, this new set of clusters might be better. So what we will end up doing is actually rerunning our k-means clustering a number of times to see if I get something better. The last bullet on page 55. So, there are a number of small changes that one can make to the algorithm that I presented to you, the exact algorithm I presented to you, that can make it better, which often means faster. So, for example, one change that you will often see implemented is that, so, when let's see here. So when I find these, let me do some erasing here. So when I find these new cluster means, what can be done is as follows. I take a look at this observation here. Let's say this is observation number 1 in my data set. I look at this observation, and I try to determine, well, do I need to reassign it to a new cluster? And in this case, I do. So then immediately, I'm going to draw a new cluster there. And then now I find new cluster means immediately before I go to observation number 2, and then look at corresponding distances. Okay? So that's just another way that this can be implemented and can actually help you find the actual clusters faster. I don't think it's really worthwhile for us to get into all these little small changes that can be made to the actual algorithm that I presented to you, but I at least want to mention to you that that can occur. And lastly then, there are actually other definitions of a cluster center, because that's what we're simply finding is a cluster center here. You could use them instead of means, you could do medians, for example. And that hopefully then allows you to think about, yeah, there's other ways to do this non-hierarchical clustering. And we just obviously don't have time to talk about all of them. I just talk about the one that's most prevalently used. Okay, so let's look at an actual data set where we can implement this. This goes back to that four observations that we saw at the very beginning of this particular section. And so here are my 4 observations. Here's what they look like on a plot. Again, to implement this method, we do not need to find all pairwise distances between observations. I just decided to do that here just for illustration purposes. This plot was actually shown in the notes how to construct it in the past. Okay. Also, I'm just going to use the actual observations themselves. I'm not going to standardize the data because this is just for illustration purposes. Okay, so let's take a look at the code to do k-means clustering. The first thing you need to do is set a seed number. Now, just make sure there's no confusion. When I say set a seed number here, I'm not talking about a cluster seed. I'm talking about a seed number from what we talked about towards the beginning of the course when we needed to simulate data, and we want to make sure that we could simulate exactly the same data. That's what I'm talking about, a seed number. So we set a seed number so that we can reproduce our results. Because again, k-means clustering randomly chooses observations from your data set to start with for your cluster seeds. So to implement k-means clustering is really easy. Use a function k-means, specify your actual data set, or what will often be your standardized data, and then say, well, how many clusters do I want? In other words, you're specifying Q. I put the results into clus.toMeans, and when I just simply print off clus.toMeans, we get just a summary of the information that's actually stored in there. What we get are the two cluster centers, or the means of the corresponding clusters. So I specified 2. So we have the first cluster is on the x-axis is 5, on the y-axis is 2.5. I have a plot of that later, shown right here. So 5 and 2.5, and also in the output, the other cluster center is at 3 and 4.2, right there. So, just from seeing this, you can see that these observations are joined together, as are these observations. Okay? Formally, how did I know that those observations were joined together? Well, on page 58, you actually have that information. Clustering vector, what that corresponds to is observation 1, observation 2, 3, and 4. Observations 1 and 2 are in what R calls cluster number 2. Observations 3 and 4 are in what R calls cluster number 1. Also, we have some information about within cluster sums of squares. But notice it says by cluster. So what that is representing, do some erasing here. What that is representing then is this part right here. So everything but the sum over the case. So if I were to sum up those two numbers that you see there on page 58, then I would get the entire within cluster sums of squares. That alone is not useful to us. We will look at how we can use that information coming up. Okay. I'll hold off on talking about this part here. Inside then this object that we get returned to us from k-means function, we have some various information that we can pull out of it. In particular, so equivalently, if I did the names function, you could see that too. So in particular, the cluster component of this object, which is a list, you can see the same thing in terms of the cluster or the observations assignments to clusters. And so I use that then to put into a data frame. And there you can see the actual observations with the clusters. Okay, so some comments, page 59. So again, the initial cluster means, or the cluster seed points, are selected as observations from the data set. That's why I specified a different seed number. Or that's why I specified a seed number so I could reproduce the exact same result at a later time if I wanted to. On page 61, if I jump ahead, right here, when I did change the seed number to something else, look what happened. Observation 1, 2, 3, 4. Observations 2 and 3 were together in a cluster. Observations 1 and 4 were together in clusters. So you can see that I did actually have different clusters. Okay, so we've already talked about the page 60 plot. I also talk about how the within sums of squares can actually be calculated with outside of the k-means function. Because we're running out of time here, I'm going to say please take a look at this on your own. I use a nice function called aggregate that allows me to find the necessary sums of squares. And also, I guess, Stan, because we were out of time, I know that's, well, that's at least a minute slow. Maybe we'll go by that as official multivariate time today, because that means I have another minute and I can talk about this. Okay, so in the output, you saw this between sums of squares and total sums of squares. That was listed there. This number alone itself is not useful. It's useful when we're doing maybe comparisons. And basically, what the total sums of squares is basically representing can be figured out from taking a look at my code here. So my data is in set 1. Here I have my first variable. I'm subtracting off the overall mean of that first variable. So I don't care about cluster memberships at all. I'm just finding each observation, each variable, corresponding data for that, subtract off the corresponding mean. I square it, and then I do the same thing for the second variable, square it, add it all up. I have my total sums of squares, which should be familiar to you because you've done total sums of squares in a ANOVA setting before. It's essentially the same thing, where you're, let's say, ignoring treatment levels, put in an ANOVA context. So my total sums of squares is 12.67. Now to find this between sums of squares, all that basically means is that you take that total within sums of squares that we saw before, subtract that off of my total sums of squares, and then I get what's called between sums of squares. Again, in an ANOVA, in a regression setting, you talk about usually three, in the very basic setting, you talk about 3 different sums of squares, and this is all that this is getting at, but in a cluster analysis sense. Please, though, do not interpret this as like an R squared, a coefficient determination. It's not the same. Okay. Now we're at 10:45 according to that clock, so we are out of time. And this also should take us up to where the next video starts. So I'm not going to add any additional information by, let's say, recording it outside of class. You should be ready to go for the next video. Are there any quick questions? Yes?
So, how does it correct?
Yes?
If they see, let's say, we take it, we correct it 1. So, we make it +3. We correct it to it doesn't change.
If the, well, you're saying, what if the C doesn't change? Well, then you're done.
Just in second.
Yeah, that can happen. If you somehow chose seeds in a particular way that was, let's say, very good in terms of the algorithm, you could be done. Okay? Okay, that's it for today.